Hey everybody, today we're going to be talking about moments of inertia. So just to start off, what is a moment of inertia? It's kind of this weird concept that is a little bit hard to visualize. From my understanding, a moment of inertia is just a resistance, an object's resistance to angular acceleration. And for this case, we're going to be going over area moments of inertia. Now, there are other moments of inertia, like mass moments of inertia, that you may have used in other classes and that you will use later on. But for this, we're talking about area moments of inertia. So if we had a block, and its centroid is right there, its moment of inertia kind of represents its resistance to angular acceleration about its own axis. Well, for the basic equation, it's going to represent it about its own axis. So if you were in a zero gravity environment and you were holding this axis out here and you tried to rotate it, how hard would this be to accelerate in that direction? And that's kind of the basic idea behind a moment of inertia. Anyway, so it may seem like this doesn't really have much to do with statics, and you'd be right in the sense that you haven't really seen it in anything you've done before. This is really going to prepare you for other classes that are to come, though, especially your strengths and materials class and some other ones. You'll be using moments of inertia quite a bit. So let's just do a basic problem here. And every object, like a rectangle, a triangle, a circle, a semicircle, has its own equation for a moment of inertia about its own centroid. And your teachers usually don't care about you memorizing those equations too much, except for this rectangular one. You'll probably want to memorize this just because you'll be using it so much, and if you don't memorize it, you'll have to look it up every time, and that could kind of be a pain. So just write out the one for a rectangle, which is 1/12 base times height cubed. And again, probably just memorize this one and look up all the rest. So if our base was 3 and it had a height of, say, 5, well, our moment of inertia about its own centroid, about this line right here, is going to equal 1/12 3 times 5 cubed. Okay, and you can probably see pretty quickly how these can start being really big numbers. Or if you have decimal points, really, really small numbers. Okay, so say you don't want to find the moment of inertia about this axis right here. Instead, you want to find it about this x-axis. We say this is y and this is our x-axis. We want to find it about this x-axis instead. Well, for this, we're going to use something called the parallel axis theorem. Basically, it's just a way of shifting the moment of inertia from this axis to this axis. So I'm going to say I naught, moment about the x-axis equals I naught, so this is I naught over here, plus AD squared. So plus the area of your object plus the distance from here to here, so the distance between your axes squared. All right, and then you just add it to your original moment of inertia, and that is the answer. So for here, you do plus 3 times 5 times the distance, half of 5 is 2.5 squared. And that would be our answer if we calculated all of that. Okay, so pretty simple for just a plain object by itself. Now say we had something a little more complex though. We had two objects that were joined together. Now normally in your book, they won't have a line dividing them. It'll just be something like that. And you can either draw a line in here yourself, or you can draw another line over here. And if you draw a line here, you can figure out the moment of inertia for this object, and then figure out the moment of inertia for this object, and then add them together. If you want to draw a line out here, you could find the moment of inertia for the entire block that you just drew, and then subtract this triangle up here. Either way, no big deal. It comes out the same no matter what you do. The one thing is, you can't just use their base equations. So for the rectangle, we have 1/12 base times height cubed. For a triangle, we have 1/36, and that is also base times height cubed. Okay, but this moment of inertia is going to be about this axis right here, and this moment of inertia is going to be about this axis right here. And we cannot add those together until we get them about the same axis. So say we want the moment of inertia about this x-axis here. Well, what we can do, in my class, my teacher always had us draw out a grid. I actually like the grid quite a bit. It helps me organize my work, and it just seems to go a little bit easier. So, the first one, we have something like this, area. We have the distance, I'm going to say y bar, because that is going to be the distance up to the axis. Then we have I naught, so the original moment of inertia about its own centroid. Then we have area times distance squared. This is what we're going to be using to shift it to the new axis. And then we're going to have moment of inertia about the x-axis. Cross. This is for object 1. This is for object 2. Okay, so I'm going to label this one 1, I'm going to label this 2, and now before we can do anything, we need distances, so that's 2 and that's 3, and then say it has a height of 3. So the area of this first square or rectangle is 2 times 3, so that's 6. Y bar, D or Y bar, is 1.5. The I naught is 1/12, 2 times 3 cubed, which is 4.5. Area times this distance squared is going to be 13.5. And then we just add these two numbers together. So IO plus AD squared equals IX. And that gives us 18. For object 2, the area of a triangle, 1/2 base times height, gives us 4.5. And then our distance is going to be 1/3 up of this total distance, so that's just 1 pi naught, 136, 3 times 3 cubed, or, yeah, is going to be 2.25. Area times the distance squared is 4.5. And then you add these two numbers together and it gives you 6.75. So the moment of inertia about the x-axis for this rectangle is 18. The moment of inertia about the x-axis for this triangle is 6.75. All we have to do is add those together to get our total moment of inertia about the x-axis, and that equals 24.75. Okay, and that's the answer that we are looking for right there. Anyway, so what you'll be doing is you'll be given just this block or some object. You'll have to divide it into different segments, find the area or the moment of inertia, and then just add them all up and keep going from there. And in some of your problems, you could have up to 4, maybe 5 different shapes within one object. Again, it's just a slow process. Make sure you stay organized, and that's going to help out a ton. That's why I like this grid method so much, just because it helps me stay organized on paper and I don't mix anything up. Anyway, that's it for these normal moments of inertia that we have here. Later on, you'll do moments of inertia by integration, and that will be the next video. I'll see you guys then.